So now I want to do another example that will be a mix of more practice with this structural induction and also a little bit of going further afield and introducing you to some cool extra things. So here is another example. Question: how many full binary trees are there? So of course there's infinitely many, but if we ask how many full binary trees with a specified number of nodes, now this is some finite number, and we can try and figure out what it is. So let's start with some examples. That is a good piece of advice if you're ever starting to try and solve a question that you don't already know the answer to try and write down some examples and see what you're getting. So n equals 1. Do we still have... Oh yeah, here we go. So how many binary trees are there with one node? There's just this guy. How many binary trees have 2 nodes? It appears that there are none, or at least none that we've written down. And then 3 nodes, we have again 1 example, and no examples of 4 nodes. And for 5 nodes, we have 3 of them. No, those are not. So these 2 have 5 nodes. This one has 7 nodes. And I think this one also has 7 nodes. Okay, so let's go back down to our work. So for n equals 1, there's just a tree with a single node. There's one of them. N equals 2, none. Oh, n equals 2, there's none. N equals 3, there's just this guy. N equals 4, again, we think there are none. N equals 5, there are these 2. And we can keep writing down examples, but let's start making some observations and trying to prove them. So let's quickly try to prove this claim. The number of nodes of a full binary tree is always odd. That seems to be what we're observing in this pattern. So let's try and prove it. As you may have guessed, we will try to prove it by structural induction. And it's a pretty simple proof. Or at least let me say it's quite similar to the one that we just did. So the base case is a single node that is n equals 1. So let me say 1 node, which is odd. Checks out. And then inductive step. So consider this tree made up of T1 and T2. And suppose T1 has N1 nodes, and T2 has N2 nodes, and N1 and N2 are odd. So this is our setup for an inductive step. This is our inductive hypothesis. then let's call this t again. Number of nodes of t is the number in t1 plus the number in t2 plus this one extra we added. So it's n1 plus n2 plus 1. And since these numbers are both odd, their sum is even. And then we see that we're adding an even number plus an odd number. Here's our odd number. So this is odd. So that completes the proof. So now what about the rest of them? So we know that for even numbers, it's always going to be 0. But what about these things? How can we figure out what these numbers are? Well, we have this recursive definition of binary trees. So let's see if we can write down a recurrence relation for these numbers that we're trying to figure out. So let's let a sub n equal number of binary trees on n nodes. And let's write a recurrence relation. So how can we make a tree that looks like this with n nodes? So to get this recurrence relation, we are going to use the fact that we can break up any binary tree into smaller binary trees like this. Or let me say, we need somewhere to start our recurrence relation. So a1 equals 1. So now I've got a foothold to start from. Or let me say a1 equals 1 and a2 equals 0. We might need 2 base cases. So now how can we go further? If we have a binary tree with 3 or more nodes, we can always write it like this, where T1 and T2 are binary trees with fewer nodes. And the only restriction, the only thing we need to make this true, is that T1 has some number of nodes. Let's call it K. Then T2, right, the number of nodes here and here has to add up to n minus 1. So if this guy has K, then this guy has to have n minus 1 minus K nodes. So how many trees can we make this way? Well, we can choose any tree with K nodes for this side, and any tree with n minus 1 minus K nodes for this side. So there are AK times an minus 1 minus K ways to do this. So the recurrence relation we get is that an, we just get this many for each k. And then we have to think about all the k's we can have. So it's the sum from k equals 1 to n minus 1 of ak times a n minus 1 minus k. So let's write down some terms of the sequence. And let's skip the even ones, because we don't care about those ones, because they're all 0. So a1 equals 1. a3 is, well, 1 times 1, which is 1. a5, let's not go through this formula explicitly, but just look at the previous terms. And this is, yeah, what is this formula saying? It's saying take this thing times this thing plus this thing times this thing. So that's 1 plus 1, it is 2. And then a7, we take the product of the outside 2, and then this one times itself, and then this one times this one. So this is 2 plus 1 plus 2, which is 5, I believe. And then if we do a couple more examples, let me blaze through it a little bit. a9 is 5 plus 2 plus 2 plus 5, which is 14. And a11 is 14 plus 10 plus 4 plus 10 plus 14, which I forget that, but I wrote it down. It's 42, and so on. So here is a method for solving recurrences that you are not going to be, this is not going to be something that I expect you to do on exams and things, but I want to introduce you to this wonderful resource, which is the Online Encyclopedia of Integer Sequences. So let's go to the internet, let's go on a little field trip. Oh, look at that. There's a practice exam posted. How cool. So, OEIS.org is the Online Encyclopedia of Integer Sequences. And the way it works is that you type in your sequence, and it tells you everything that it knows about it. So 1, 1, 2, 5, 14, 42. These are the first couple terms of our sequence that we computed. And OEIS has found a match. It appears to be the Catalan numbers. So what is this telling us? First of all, you've got up here basically an explicit expression for these numbers. So that's going to be very useful if they turn out to be the right ones. There's also a million different combinatorial interpretations. In fact, if you look at this first entry, a very large number of interpretations are known. This is probably the longest entry in the OEIS. So maybe it is not such a surprise that we found the Catalan numbers. Okay, and we can look through the article. Okay, you can see that it's very long, lots of references, lots of links. But the thing that I want to point out is if we keep scrolling down, we should get to some formulas. And one of them, if I can select it, is exactly the recurrence relation that we have just found. So this is saying that the nth term in the sequence is the sum of the product of the kth term and the n minus 1 minus k term. which if you remember, is exactly the recurrence relation that we wrote down. So there you go. The number of full binary trees is indeed given by the Catalan numbers. And if you want, you have different formulas, which actually give you a closed form for the number, for these numbers. So this is a very nice resource if you are ever trying to work with integer sequences. It is a great place to go.